Okay, good morning. How's everyone today? I hope everybody's doing well. Gonna try to finish up chapter 2 today. So got a couple of slides to get through. Um, I'll finish up this first set of slides, then I'll go into the water and pH slides. But again, not a whole lot to get through to complete chapter 2. So again, we've kind of got to the idea, we've gotten to the point where we've talked about bonding. Let me see, where did we leave off? We left off with the summary of the 3 bond types. So looking at covalent bonding, we're looking at ionic bonding, at hydrogen bonding, trying to learn the differences of the actual bond itself, how it works, how it's different, the strength of the bond, why some bonds happen, why other bonds happen. So that's, again, an important foundational, very fundamental type of knowledge that's going to help you for the rest of the semester here, right? So again, biology being supported, being sort of built around, built upon the chemistry and physical basis there, right? So that's where we left off last time. Let's move forward. I'm not going to spend a lot of time with this, but we did talk about atomic masses, how much one atom weighs if we put it on a little tiny scale. So one carbon has an atomic mass of 12. So one carbon atom placed on a scale would give us 12 atomic mass units. One hydrogen weighs 1, so it would weigh 1, right? Now, we start introducing this idea of a molecular weight, right? So we know there's a difference between an atom, one single element, one single atom, and then a molecule, which is a combination by ionic attraction, by covalent sharing. These are going to be bigger. So how do we estimate the weight of the molecule? Well, it's actually quite simple. We add the individual atomic masses together. So for example, water, we know that oxygen weighs 16, hydrogen weighs 1, but there's 2 separate hydrogens, H2O. So the molecular mass for water would be 18. So again, it's just the sum, the summation, the adding up of the individual atomic masses, right? So these are still small molecules. The more individual oxygens and nitrogens and carbons and hydrogens we add, the bigger and bigger and bigger and heavier the molecule becomes. So I think there's a homework question that asks you to calculate the molecular mass. Well, that's what it's asking right there. So you add up the individual atomic masses, not the atomic numbers, not just the number of protons, but the atomic masses. So protons and neutrons on the periodic table, it'll be not the top number, but the lower number, the bigger number that's down below, yeah? So something else, just the notation. So we got to kind of speak the language of chemistry, right? So in the book and in my discussions, we're going to start hearing about reactants and products. So chemical reactions occur when atoms combine or change partners. So reactions are written as equations. Ooh, welcome to algebra, right? So it's not a big deal. If you don't like algebra, no worries. It's not that complex here. But reactions are written as equations with reactants and products. So the way we would read this notation, reactant 1 plus reactant 2 yields a product or products, right? So we're constrained by a very important physical law. So chapter 2 and then chapter 8 gets back into it again as well. The conservation of energy. So that states that energy cannot be created, energy cannot be destroyed. All we can do is transform, change the type of energy, right? So when we apply the conservation of energy law to our reactions, the way we do this is we say, well, whatever we start on the reactant side with, we got to have the same on the product side with. So they're just going to be kind of switched around. So if we look at this notation here, If you remember the notation, 2 out in front, that means we have 2 of those things. So we have H2, covalent bond. I hope you understand why that's stable, H2, and the second H2, right? White represents hydrogen. I don't know if you covered this in lab yet. White represents hydrogen, red represents oxygen in the ball and stick models, right? So we have H2 twice, H2, H2. So we have a total of 4 individual hydrogen atoms. So for us to conserve energy, we got to have 4 hydrogen atoms on the right-hand side of that equation as well. So 1, 2, 3, and 4. All right, so good. Conservation of energy was achieved. On the left-hand side of the yield sign, we have 2 oxygens. It's a double covalent bond, O2. And on the right-hand side of that equation, we also have those 2 oxygens. So everything is okay, it's balanced. Energy was conserved here. So the reactant 1 plus reactant 2, so the reactants plus reactants yields the products. So that's how that notation will be written. In this situation, the arrow is one way, right? It's just one directional. That means that once we convert into the products, that's a stable product, and that the product is done, right? There's sometimes going to be written a reversible type of arrow, where the arrow would go one direction and then also come back the other direction. So 2 directional arrows, meaning we can form the product, but the product can break back down to the individual reactant forms. So you'll see that a little bit later in the semester. So if you, I don't know, maybe had a barbecue this weekend or something like that, you actually performed a chemical reaction. You're a chemist. So in this situation, we have our yield sign. So to the left are our reactants. To the right are our products, right? So we have the propane gas, 3 carbons, 8 hydrogens, and 10 individual atoms of oxygen, right? 5 O2 molecules here, right? So in order to conserve energy, we say we better have 3 carbons, 3 black models on the right side. 1, 2, 3, all right, good. We better have 8 hydrogens over here. 1, 2, 3, 4, 5, 6, 7, 8 white molecules or white atoms. So 2H times 4 gives me 8. I better have 10 total oxygens. Well, I have 1, 2, 3, 4, right? 4 oxygens. 1, 2, 3, 4, 5, 6. 3 times 2 gives me 6, right? So this tells us it's a one-directional reaction. Propane mixed with oxygen gas, we give it a spark, and it generates then carbon dioxide gas, water vapor, heat, and light. And that's a chemical reaction, right? A one-directional reaction there. So again, the key point here, don't memorize this individual reaction, just understand conservation of energy, the symbolism, right? So if I have a number out in front, if I have a subscript, what that means, how that's different, right? That's going to help you out in lab and then also in the homework. So chemical reactions. Isotopes are a little sort of oddball category, and I've never met your book author Freeman, but Freeman seems to be quite ADHD. Like he covers one thing and, oh, I forgot to cover this. So he goes back and cover another thing, and then he goes forward and goes back to another side aspect, and in this trajectory and that trajectory. So isotopes are kind of similar, right? Isotopes, he just kind of splashes them into the chapter. They do have significance. They're just another bit of information that you have to know, basically, that you'll see on the homework again. So isotopes are atoms of the same element that have different atomic weights. So atoms of the same element that have different atomic weights. So they're overweight atoms, if you can think of them that way, right? So they're the same number of protons. It's the same atom, same number of protons, but different number of neutrons. So I'll come back to that bottom point here. So carbon is very common. It exists in an isotopic state, very, very common. Another one is hydrogen, right? So I think this shows it a little bit easier to tell. So how do I know that's hydrogen? Because it has one proton, yeah? One proton can attract one electron. It's electrically balanced. Hydrogen has an atomic mass of 1, right? So in this situation, that's the normal elemental form of hydrogen. Now that's normal. If you notice here, now we have hydrogen with an atomic mass of 2. And this is not typical. Normally the proton numbers are reversed, but I don't know why they have the upside down symbolism here. But so we have 1 proton and 1 neutron. Now hydrogen doesn't really need a neutron. It just, because of some force of energy, a volcanic eruption, a lightning strike, maybe an artificial investment of energy in a lab setting, an extra neutron was crammed into that atom. So it's the same hydrogen, but it's heavier. It's got this extra neutron in there. The same thing can be done again. So still hydrogen, but now it's got 2 neutrons. So this atom is still hydrogen. It has the characteristics of hydrogen. It's just heavy. It's just overweight. If you're a Marvel fan, if you remember Thor, all lean and in shape, and then later Thor is still Thor, but he got overweight, right? So same thing, but just heavy. So this hydrogen will basically move from place to place very slowly compared to this other. Now, if you can envision, if we were in a regular semester, you'd have this big backpack, or maybe you have a big heavy purse, or you're just carrying something very heavy, you're walking around, you're gonna go a little bit slower. And when you get to your location, the first thing you wanna do is get rid of that heavy backpack or that heavy purse. Yeah? So same concept here. Hydrogen wants to get rid of these neutrons, and it will do so. As that neutron passes through that energy shell of the electron, it will release a type of radiation, right? So isotopes, most isotopes, we're gonna say, are radioisotopes. When those neutrons go through that electron energy shell, through that valence shell, they release either a type of alpha, beta, or gamma radiation. And that can be bad, or it can be used for medical purposes. A lot of the radiation therapy, chemotherapy for cancer patients is derived by artificial isotopes, and these isotopes are injected into a person to, maybe they have a problem with their thyroid, maybe they have some sort of chemo or cancer that requires chemo. So these are the types of sort of quote chemo drugs that are given to the patients, these isotopic configurations here. So isotopes. Carbon can also be used to date dinosaur bones, old pottery that they find. It's a common sort of substance out in nature. And again, carbon, this is a normal carbon, carbon 12, because it has 6 protons, 6 neutrons. Carbon 13 has an extra neutron, and carbon 14 has still even an extra neutron. So that's not stable. This will degrade back to carbon 13. This will degrade back to carbon 12 eventually. It takes a long time, but in that process, radiation is released. So the idea of isotopes. Okay, so I'm going to slow down a little bit here with functional groups. Functional groups are something that you're going to have to get familiar with, right? You're going to deal with functional groups in chapters 3, 4, 5, and 6. So I need for y'all to get a good grasp on functional groups. Functional groups, as implied here, are groups of atoms. So little molecules, little groups of atoms, little molecules. And they're going to give a particular function. The best analogy I can give you here is if we had Mr. Potato Head, right? Envision Mr. Potato Head. So Mr. Potato Head has detachable parts, right? So if I detach the arm of Mr. Potato Head and put a pair of eyes on the side, right? So it's going to change the way Mr. Potato Head's going to function. Instead of looking straight ahead, he might look this way. Or I take Mr. Potato Head's hat off, and I put now an arm on the top. So it's going to change the way that Mr. Potato Head functions. So he can now reach higher things there, yeah? So this is the idea of functional groups. The groups of molecules that can be added to the molecule, a bigger molecule, to change the functionality of that first initial molecule. So a couple of functional groups I want you to see. So hydroxyls, right? These are the first one. A hydroxyl is a combination of an oxygen and a hydrogen. They're like buddies. We tend to see these a lot of, most of the functional groups are going to be buddies, kind of like when you think of salt, well, there's always pepper, right? When you think of, I don't know, cookies, maybe you think of milk. Jack and Jill, or maybe you like Jack and Coke. I don't know. So things that always kind of go together. Right? So green eggs and ham, right? Something like that. So when I have an oxygen, normally, very high percentage of the time, we have it teamed up with a hydrogen. They're both very common elements. So oxygen and hydrogen, and then connected to something else over here. And that would designate then a hydroxyl functional group. Hydroxyls are very critical in the formation of carbohydrates, right? Most carbs, we're going to get to these in chapter 5. Most carbs have the basis of carbohydrates, right? That's where carbohydrates have these functional groups associated with them very commonly. If you know something about carbohydrates, sugars, if I put, let's say, the carbs in a agave plant, the carbs in potatoes, the carbs in corn, the carbs in barleys and hops, the carbs in grapes. If I put these in a container, seal them off, no oxygen, these hydroxyls start to be released, and we consider those to be alcohols, right? So these are alcohol. Hydroxyls have a very important biological role. If you consume a lot of hydroxyl groups, that's what gives you the buzz. That's what basically gives the inebriated sort of situation for the human body. So important biologically. Humans do a lot of dumb stuff when there's a lot of hydroxyl functional groups in their system, right? Many humans are conceived when mom and dad have a lot of hydroxyl functional groups in their system, right? So very important biologically, hydroxyl. Carbonyl, the second one, right? So carbonyl is going to be a carbon double bonded to a oxygen, and two separate, whatever else, whatever other molecule or elements are there. But this double bond to the oxygen designates that carbonyl. Right? And we do typically find them by themselves, but more realistically, we're going to find them in this format, the carboxyl. So in chapter 3, we get into proteins, and we can't have proteins without amino acids. So we have then this idea of the carboxyl functional group, which is a carbonyl and then a hydroxyl. So there's a hydroxyl with the carbonyl. Collectively, we call this mess the carboxyl. And again, the aminos, we have a nitrogen with 2 hydrogens, NH2. So that designates my amino functional group. Sulfhydryls, we don't deal with too much. Methyls are very boring in chemistry. They don't do very much. But the last one that we're going to cover, a little red star there, phosphates. Phosphates are going to be very, very significant as we get into more discussion on energetics, on lipids, nucleic acids. So phosphates are very critical. It's a phosphorus with 4 oxygen bodyguards all around. Right? There's some ionization, some have an anion there. It is a stable configuration, sort of phosphorus with its entourage of oxygens all around. So these are the functional groups you'll need to know for the homework, and the functional groups you'll need to know for the upcoming chapters as well. So hydroxyl, carbonyl, carboxyl, amino, and phosphates. And I don't know, maybe you've touched upon these in lab too. I'm not quite sure. So same concept, different notation. Right? So here we have the amino group NH2 or H2N, a nitrogen with 2 hydrogens, amino. We have a carbonyl with a hydroxyl, that Cu, right? This Cu we designate then as the carboxyl. And it's symbolized like that to let the student know, hey, this is a functional group. It has an impact on the functionality of the overall atom. So you saw these pictures before, right? We said that chemistry is important in biology. You saw these pictures, but now let's analyze it with the knowledge of functional groups. So, ooh, what do I see down here? Ooh, I see a hydroxyl, another hydroxyl. What about this? C double bond to O, that is a, I hope you said carbonyl. How about this? NH2, that is a, I hope you said amino group, right? Another hydroxyl. So yes, they're big, ugly molecules, but once we start to dissect them down a little bit, we can start to see, well, they're familiar little combinations, familiar little groups of functional groups that give us an idea what this molecule does, how it works, right? So the functional groups. So true or false, there is a carbonyl in this particular aspirin molecule. That is a true statement, right? There's our carbonyl. True or false, there is a an amino group in this particular molecule. False, there was no amino. We have just a carbonyl and we have a hydroxyl, right? But this is the kind of stuff, the homework, and this is the kind of knowledge that you will be required to know, for the homework and for the remaining, chapters and material in the course here. So venom, right? Snake venom. There's our familiar Cu, right? I don't know if you can see that Cu. Here we have a carbonyl. This is close to a amino, but not quite. It's only got 1 hydrogen, so that would not qualify for the amino functional group. But again, carbonyls and carboxyls present there. And basically we have, again, a molecule with multiple functional groups, right? Some hydroxyls again. What do we see? Hydroxyl. So again, this is how you would be required to know this information right now. The recognition, being able to recognize the particular functional groups in their locations in bigger complicated molecules. So with that, that will conclude this little section, still in chapter 2. I'm going to stop this one, and I'm going to get into the discussion on water and pH, and then that will be the end of the material for chapter 2. Right? Chapter 2 is kind of a long chapter, a lot of things to cover to set the framework for the rest of the material. Right? So let me stop there.